We also diffraction setup in which we use low pressure sodium vapor lamp and a diffuser to observe a monochromatic view of the droplet and the evolution of its thickness over time. In this case, we also use the droplet release mechanism as mentioned earlier. Some experimental measurements we use are syringes, micropipettes, and graduated cylinders for more controlled variables. Going on to our theoretical model. First, we'll be explaining alcohol evaporation, in which we think is the main principle of the overall phenomenon. For our geometry, we'll be introducing the evaporation rate of alcohol, the width of the rim, the minimum thickness of the droplet expansion, the initial mass fraction of alcohol at the center of the drop, and mass fraction of alcohol at the rim of the expansion, in which we call the rim right before the fermentation, and the velocity of air running flow, radius of droplet, and depth of the oil layer, which is the depth of a hydrophobic liquid. Some assumptions that we made for the first theoretical model are, first, the thinner film of the droplet is caused by alcohol evaporation, in which means that we believe that alcohol evaporation is the main parameter that's changing the thickness of the droplet. And then the evaporation of water is negligible throughout the experiment because it is relatively slow in terms of the time scale that we measured in. The ambient room temperature remains constant throughout all experiments, and lastly, the impact of water-based diet is negligible. So here we'll be introducing the Maragonian flow first induced by alcohol evaporation. When we release a droplet, we believe that there's more alcohol in the center, and there will be less alcohol starting from the rim or the side of the droplet as it starts to expand. This is because, according to our geometry, the center of the droplet is the thickest part, and as it gradually expands on top of the oil surface, it will become thinner. And now, although the evaporation is in a constant speed, the overall portion of the alcohol evaporated will be more significant from the side compared to the center of the droplet. In this case, since water has a significantly higher surface tension compared to alcohol, the more alcohol at the center of the droplet will cause it to have lower surface tension, and the edge of the droplet will have higher surface tension due to the higher concentration of water at this part of the droplet. And this surface tension gradient is the main driving factor of the Maragonian flow, leading to the expansion of the droplet. As we mentioned, evaporation is the main driving parameter. Now we're getting to the evaporation flux as to how exactly evaporation affects the droplet expansion and its eventual instability at the end. To calculate the evaporation flux, we use Fick's law to symbolize the diffusion of particles from the process in which alcohol is evaporated into air. And then we use also, due to the mass conservation across interface, we can calculate the exact alcohol evaporation flux and equate the two equations together for a more accurate calculation of the alcohol evaporated during the expansion process. In terms of its interfacial energy balance, for negligible heat conduction and convection in air, the interfacial energy balance is calculated as follows, in which we consider the liquid conductivity and the alcohol evaporation throughout the process. In terms of alcohol evaporation itself, we know that the alcohol is evaporating at a constant rate, and then the spreading parameter in which we introduce how fast, like the certain scenario that the droplet will actually spread, we call that the spreading parameter, and technically from literature, it means the surface tension of the oil air must be greater than the surface tension of mixture and air and mixture of oil combined. Only under this scenario, the critical value will allow and lead to the eventual expansion of the droplet. So, like I mentioned earlier, due to the surface tension gradient and the concentration difference of alcohol, we will see a higher total mass evaporation flux at the rim, and there will be a greater evaporation flux at the center of the droplet. Moving on to our second theoretical model, we'll be talking about the interfacial tension and shear stress. In addition to our previous geometry, there is a higher concentration of alcohol in the center and lower concentration of alcohol from the side, which we previously classified as the major driven parameter of the expansion. Now we're introducing the evaporation of alcohol. And in this theoretical model, we'll be assuming that the ambient room temperature is constant, the dropping height remains constant, the dimensions of the oil plate remains constant, the effects caused by ingredients of the water-based food dye is constant, and the evaporation of alcohol during the dropping process is the release process, in which we drop it from the release mechanism to the oil. That short process is negligible, and lastly, the evaporation of water in this experiment is negligible. As previously mentioned, Maragonic flow is driven throughout the process of alcohol evaporation, in which in this case we can start to use scaling law to approximate the total alcohol evaporated during the process. Here we have a time scale of the experiment. In the revolution equation for the height as a function of radial coordinate r and time t could also be classified, in which we consider the pressure gradient, the surface tension gradient, the alcohol volume evaporation flux, and considering these parameters, we can calculate the change of height over time. The pressure in the droplet is dominated by surface tension. Therefore, the pressure can be given by Laplace pressure. Knowing the pressure, we consider all the dimensions of the droplet and the oil itself, as well as the characteristic of the alcohol and its evaporation. So now we can, using scaling law, we solve for a characteristic radius of the droplet expansion. That's a time scale based on the convection of liquid from center to the edge. The restrictions apply because certain parameters are not constant, and the estimated maximum radius and correlated time to reach that maximum radius. The viscous stress is also determined in the kinematic viscosity of oil, which we can determine the tangential stress applied to the droplet of oil. In this case, you see that the decreasing depth of oil will hinder the droplet expansion. Moving on to our experimental verification, we first did a preliminary experiment on changing the volume and the concentration, in which we see that making the higher concentration of alcohol will have a faster expansion and a larger radius, and increasing the height of the oil will reach to the exact same result. We then consider the critical point of the spreading parameter. In this case, we use ethanol as an example. We see that 50% does not spread, while 0.9% does spread. To further investigate the critical value, we investigated all the concentrations tested for methanol, and then we eventually found out that the critical value for the methanol droplet to expand is 90%. We also varied oil depth, in which we concluded that increasing the oil depth will help it to expand faster and reach a higher, larger radius. We also varied solvent, in which we tested isopropanol, ethanol, and methanol, and this allowed us to conclude with a different radius compared to the solvent themselves. Lastly, we had an interfacial tension measurement that we used to consider the interfacial measurement of all the components themselves. And from here, we can conclude with the interfacial tension of the oil and isopropanol. And after testing all the types of solvents, we realized there is a difference in their interfacial tension, which is leading to the different costs of their spreading parameters. We have the experimental verification of varying the concentration and the oil depth, which include various in-depth depth of electrical liquid directly impact the size and speed of expansion. Lastly, regarding the Plato release stability at the rim of the droplet, we can conclude that the volume of the main droplet can be calculated, and with the main droplet being calculated, we can use a simulation to predict that with the change of isopropanol alcohol, the increase in concentration will lead to an increase in the number of droplets, but a decrease in the size of the droplets. Here is a video of our microscopy for 50% isopropanol and a video of 70% isopropanol, in which this case we can see that the 70% isopropanol does have smaller size and more droplets, which match with our theory prediction. The key parameters we varied in our experiments are the initial concentration, droplet volume, depth of oil, and type of solvent, in which we can conclude that with varying these parameters, we can conclude with different size of the droplets and different radius of the expansion, as well as the time it takes to reach that final expansion.
Okay, thank you. For your experiments, you showed most of the mixtures being with what type of oil for the base of the batter.
So we investigated the change in vegetable oil and baby oil, and because of the difference of surface tension of self, which is the surface tension of baby oil in the air and the vegetable oil in the air, we did investigate different phenomena which affected the final extension and the rates in which it extended. My fifth theoretical model, because I was going to focus on the variation of the droplet itself, I designed photographs for the extension of change in oil. However, it's very similar because essentially the change in oil just changed one of the parameters in the spreading parameter, like one of the variables.
We just want a short answer. So which oil?
Oh, okay. The image of the oil?
The question.
What type of oil was the most effective then?
Vegetable oil was the most effective in terms of having the largest radius.
That's it. Next question.
Under what conditions would the droplet not break?
Break is to fragmentation?
Yes, explode.
Yes, because the fragmentation is caused due to instability. So if the alcohol concentration is very low, and it doesn't have enough conversion force for it to actually have that pushing force and stopping force of wedging and dividing to form the instability. So therefore, low concentration of alcohol will hinder the fragmentation.
Are there other ways in which the droplet can explode, being not like the one you showed in the videos, like other behaviors you can take? Other behaviors you can have in the moment of exploding?
By releasing it at a different, like let's say you inject it into the oil, and after it flows up, that process will actually hinder its fragmentation. So vice versa.
Thank you.
Okay, we have 3 minutes for you to prepare your report. And next, remember to enter the name of your
drop and the behavior it has when it explodes due to the experimental setup. They deeply described the water alcohol surface tensions and how they measured everything for the experiments, and included experimental results down to a macroscopical level, which makes it be more precise. Those would be what I consider to be the strengths of the presentation. However, there are some things that I think could have been present in the presentation, like different types of water mixture, which is also something I consider a weakness, due to the problem saying example water alcohol mixture and example vegetable oil, and the opponent didn't try at all showing hydrophobic liquids apart from the baby oil and vegetable oil, and also all of the examples of the water mixture included a water alcohol mixture, specifically with the, I think it was 2 or 3 types of alcohol they mentioned in the presentation. Another thing I want to say is that the graph didn't really show an error margin of the measurements of the experiment compared to the theoretical part, so it's a little bit hard to see where the theory gets apart from the actual experiment. I think it would have been interesting to explore how the position of the droplet container affected, seeing if they control it being in the exact center of the container, how it affected it if it was more to one side, or the border effects of the surface tension inside of the container. Other weaknesses listed down in this presentation are the exact amount of droplets, as they do mention that they are augmenting as in the graph they show how the amount of droplets could go up or down, but there wasn't exactly something that showed how many droplets there were. The size of the droplets are not mentioned specifically, neither are the shape they take, if they are, not an exact circle, but how it is defined. And the other thing I wanted to mention was that okay, so for the last part there was a simulation, and it wasn't really showed if it matched and how it matched the numbers of the actual experimentation, if it was made to find that part. Other behaviors of the droplet, apart from exploding, weren't explored, like the case where it doesn't explode, though she did answer it, it wasn't in the presentation. And other shapes where it can explode weren't there either, like it not being exactly from the center of the drop and extending outwards, and the behavior at the edge of the ring of the droplet. That would be all. Thank you. We can move on to the discussion.
Okay, so you
I'll start the discussion. Not yet, but if you want to, first I want to ask you, did you consider the border effects of a container where you could have the oil bath in the expanding of the droplet? Since the surface tension is so important, the border effects, for example, if you have a circular or a rectangular container, would affect the expanding of the droplet?
Yes, so we consider the compelling pressure. That's why in our assumption we specifically mentioned that we use the exact same dimension and shape of the light, which is the exact same plate, to limit the possible variations that this parameter may bring to the overall phenomenon.
How do you think it would affect if it had another shape?
I think based on my previous experiments, I don't think changing the as long as it's like a flat and perpendicular rectangular or circular shouldn't change the phenomenon overall that much, and I believe all the parameters should be within the error bars, even if you construct a different shape of container. As long as you keep the other parameters as constant, then I don't think the overall result will be much different.
Okay, now another way in which a droplet could have fragmented, if you had at the beginning, the initial droplet it could, instead of starting going outwards in this way, it could split out into separate sections like this. How would that happen?
I can show you our experiment for that specifically. As you can see here, we can actually observe sorry. We can actually see two different types of the emission of fragmentation. And this, here we see the stream seems to be more like independent and it seems to be circular upward. As here we can see like it's a stream that gradually split into three common other streams that continuously to emit droplet. This is typically caused by the variation in concentration of alcohol, which leads to the different wavelength of the rarely instability itself.
What are the types of alcohol, or not alcohol, but what are the types of liquid can you have mixed with water for the effect to happen?
So you have to use miscible solvents with water, and throughout our experiment we actually tested acetone as well. But then we realized that acetone is soluble with both water and oil, which actually affected our experiment in measuring the surface tension. That's why we didn't include acetone in this. So therefore I can conclude that if you want this to happen, first of all, this second component of the water, it must be miscible with water, and then it cannot be soluble with oil, and it has to be able to wet the oil surface in order to actually perform the wet and wetting and form the railing stability at the end, so we can actually see the fragmentations.
Thank you. In your experimental part, what was the minimum height of oil or just surface you had to have?
The minimum height we tested was 5 millimeters, and the highest I believe was 15 millimeters.
Below and above that, what happened?
Sorry?
Below and above that.
So actually at 5, it's already spreading at a really slow, and we tried below 5 millimeters. The concentration that's supposed to spread will stop spreading. So that we can also conclude that for, other than the critical value I mentioned for concentration of alcohol, there should essentially also be a critical value of oil depth, in which once you go below that oil depth, you will no longer see the droplet expansion. But like this droplet may still be able to expand on a higher level of oil.
Thank you. If you were to heat the setup up to a point where the water is also evaporating, how would that affect using journals?
The overall radius should be smaller due to the evaporation of water. And however, even if you heat up the water is like alcohol still evaporates faster, and water after alcohol leaves water itself still can't wet the oil. So the overall phenomenon will not change.
Now, going back a little bit to the position of the droplet inside the container. When you have, for example, a container like this, if you were to drop the droplet over in the side,
if you drop the droplet here, let's say the droplet this size is supposed to expand to this size, then you will actually see it first expanding to all direction. And then at here, it will start to be like, it will be stopped due to the barrier of the container, while this part continues to expand to its supposed size. And this part, you can see it's starting to, it's still pushing outwards. So actually at this area, you can see a clump of the fragmentation very closely packed together due to the continuous pushing, while here it is still emitting regularly.
okay, but for the liquid that were to spread in this part, there will start being a concentration in the ring over here. Yes, like it would start gathering beside the edges.
The cohesion between the particles itself will not cause it to have such extreme like deformation. It will still be overall circular, so it will more be like this, like still circular inside. It will not just continuously to expand on the side.
minimum height to which a droplet can go?
The minimum height for all concentrations are different. For me, I tested 90% methanol. I remember the lowest height for it was 5 milliliters itself. I did vary it to 4 milliliters to 6 milliliters. They both, 6 milliliters, it continued to spread, and 5 milliliters was exactly when it stopped. It may be in a range of 25 to 6 milliliters, but I did not go to smaller.
If there were too high of a volume of the initial droplet, what would happen?
Too volume.
Too big of a volume for the droplet.
So like variations in volume of the droplet.
Yes, if the volume was very big.
So as you increase the volume of the droplet, it will actually expand at a faster rate and reach a larger radius. As mentioned, we do have a graph showing this here. Right here, we did vary the volume and the concentration. So you can see that as you increase the volume itself, even if the concentration remains the same, so in this case, gray and blue, the larger volume will still have a longer expansion and a larger radius.
For the simulation you did of the droplets, how did that compare to what actually was happening?
You don't mind, I'll just go to my simulation slide. So some ways that you can actually, some ways that you can use to compare your simulation and the theoretical result from the simulation is that you can use image analysis to eventually get the size contribution of the fragmentations. But due to the limitation of access to image analysis and a high resolution camera, we weren't able to actually perform a very accurate version of the size distribution. But we did test out one set in which we got a relatively accurate histogram of the size distribution of an expansion and its fragmentation.
Does the turbulence of the liquid can affect the phenomenon if it were to be in a turbulent situation?
Yes, if you shape the plate, the expansion itself will not stop. However, the resulting shape of the expansion may be affected due to turbulence flow.
And now, how do you assure that the evaporation rate of the alcohol is constant?
For the evaporation itself, due to its chemical property and we remained our room at a constant temperature and humidity, constant humidity. So it should be at a constant evaporation. Even if not, it should be negligible.
If it were, are you sure that would be negligible?
At a room that with all constants kept, the evaporation rate will be constant. However, the evaporation flux will not.
Okay, thank you very much. That's very interesting. And now it's time that you have your 1 minute to summarize your whole session.
I found that the presentation of the reporter was very complete with the necessary parameters investigated. However, there are some things that were missed. Like, as I mentioned, the position of the droplet container, even though they did answer what I asked about that in the discussion, I think more experimentation about this should have been done since there is so much focus being put in the surface tension of the liquids. There are also other ways in which a drop can fragment, and these weren't explored or considered inside the theoretical model. Like the droplet not expanding from the center outwards, but just to one side, even if it was in the center. Even though it was explained later, the focus being only in alcohol and on 2 types of oil seem a little bit, lacking, since the problem doesn't specify it has to be that, and different liquids could have different effects. Thank you.
Thank you very much. And now we go with some questions from the reviewer. Both the
Oh, okay. So for the reporter, how large is the petri dish? Is the petri dish the one plate that holds the droplet?
We had a plate that was, I think, 50 centimeters by 50 centimeters.
Oh, how large is the radius of the droplet?
The radius of the droplet itself is within 10 centimeters.
So to the opponent, do you think that's the size of the petri dish is enough to ignore the effect of the border? Do you think the size of the dish is enough to ignore the effect of the border?
It will depend on the volume of the droplet and in the point where you drop it. If you drop it to the
Okay, thank you.
where it
Okay, so the reporter used the radius value theory to calculate the size of the final droplet. Do you think that's the applicable theory to this problem? Do you think the reporter can use the radius value theory?
Yes.
Okay, thank you. And to the reporter, did you actually use the fluid equations in your theory? Because I noticed that you used the theory from the literature, and that was the scale law. So did you actually use your own theory?
Yes, for our own theory, we used the Navier-Stokes for the velocity of the Maragall flow itself. And for our theory, the scaling law wasn't an accurate, this is approximation based. However, it did provide a more accurate version. So we continued with that theory and we investigated the strength.
All the graphs will plot with your own theory.
Yes.
And could you briefly explain what the role of the oil is?
The role of oil is provide a medium to allow that allows to show the differences between the characteristics of water and alcohol.
Thank you. And this question is also to you. Do you think that if we have a mixture, for example, for acetone, do you think that they won't fragment for acetone, or why is it relevant for the question according to the problem statement?
It will still fragmentate, but from our observation, the critical value is different, and the size and fragmentation distribution was also different. So I think it's important for the problem because it has to maintain it asks you to investigate certain parameters that affect the.
Okay, thank you. And did you measure the concentration at the edge of the droplet?
Yes, not at the edge of the droplet. We only measure the initial droplet, initial concentration.
And to the opponent, do you think that's appropriate? Do you think the reporter should have measured the concentration at the edge of the droplet?
Yes, I do, because they focus a lot on that part of the experiment and it would have been interesting.
Okay, I agree with you as well, because in order to solve the relative equation, you need to know a certain percentage of the edge, so you can't just assume it to be a constant. Thank you.
Alright, so we have your preparation time for your review.
Good afternoon, ladies and gentlemen. I'm Dr. from Team Taiwan, and I'll be reviewing problem number 10, droplet explosion. So for the report, they have an excellent experiments out. They have microscopes for observation, and they also have a chromatic microscope to help them observe the thickness of the mother droplet. So the strings are there. They have the control angle of the plate, and they have the control release height and the control droplet volume, and they can observe the thickness of the improvement that they use that. And although they already have a monochromatic light for the diffraction to form, I don't think they need to use the dye, which causes an extra effect for the theory. And also they did not show us how the thickness affects, how the different parameters affect the thickness of the droplet. And for the theory, they explain the Marconi flow, and this happens because the thickness of the droplet is different, but the aerial evaporation rate is the same. So there will be a surface tension gradient. So there will be flow from the center of the droplet to the end of the droplet, and they also show us an interfacial energy balance, and they use this to explain that there is a critical concentration for the droplet spread. And they also show us a scaling law, and they improve the size of scaling law with their analytical solution. And for the size of the final droplets, then the droplets were rejected from the final droplet. They use the Reddick Tattoo equation. But the pros are that they mentioned they have different evaporation rates for different concentrations, and they also use this theory to solve the final droplet size. So I think the improvements are that they did not improve the effect of dye, and fluid equations were not used for the real tattoo equations. And also, I think they need to justify why they use radius calculation for this. And for the data analysis, it shows the strength interval value, the mother droplet radius, what changes with the time, and the dollar droplet size. So the mother droplet radius matches tells us that their theory is very good, and they confidently predict the final droplet size. But for the large uncertainty for interfacial tension, and then have no justification for the use of radius tattoo. That is because radius tattoo only works for the same surface tension, but now the droplet actually has contact with the air and the oil, so I don't think this can be used. Okay, so for the review of position, we mentioned the different types of mixture conditions and the amount of droplets. And within they found critical parameters because having different mixtures changes the surface tension, so that should also affect the final droplet size. But they didn't point out why radius tattoo could be used to calculate the final droplet size, and they didn't mention the lack of discussion on the role of the oil and whether having a very thin oil could actually if the reporter could predict how high the oil should be for the final droplet to form. And during these discussions, they talked about the different droplet type, the order effect, the volume of the initial droplet. So they did mention that if the droplet will drop near the edge, it might come together, but they didn't explain the importance of different mixtures. Okay. And there were not enough improvement suggestions. So for the key discussion, the opponent first asked how it affected the border, and the person said there's no effects, and we clarified in the short question that the size of the is very large, so we think the border should not have a significant effect. Okay. And someone has said how different types of liquids should affect the phenomenon, and the report said it's tried acetone, but it cannot be visible with the oil, so that it is not important to this question. It is visible with oil, so it's not important to the question. But we think spreading happens between this droplets halfway between being visible with the oil and being visible with the water. So this is a relevant parameter. And finally, we only asked about a large droplet, how the initial droplet volume may affect the size of the recorder, that they expense at a faster rate and expense at a larger size. And this is described by the side theory that shows the data. We asked about questions about pressure from the edge, and according to this, I think this cannot be informed. You don't need to know the concentration of the edge to solve the radius tattoo. And the role of oil is that it provides a track, but with it, you need to investigate why.
And how it impacts the fragmentation and the size of the final droplets. I think the working on. In addition, for our own contribution, I believe that I further investigated the surface tension, the surface interfacial tension between the fluids themselves, and that is not the literature we have seen so far. These only experiments allow us to better understand the problems and understand the phenomena themselves, in which helps us to understand the theory and apply it to the theory, which I think is a great development for this problem and throughout our investigation. I would like to thank my opponent and the reviewer for the discussion today. The problems that we've discussed definitely have brought us further insights on the problem, and knowing the future development criteria, it allows us to learn the problems better. Lastly, I would like to conclude with a final conclusion of our discussion today. I think our discussion on the parameters and the theory itself is very meaningful and valuable. Thanks so much. Like the depth of the oil layer? Yes. Oh, so it's the height. What is the role of the layer and the depth of the oil layer in your experiment? Oh, in my experiment, we varied from the range of 5 millimeters to 15 centimeters, and we investigated the size and the distribution with the variations. Sorry, I didn't. Where did you mention it in your theory and experiment considered? Okay. Let me share my screen share. And also the reviewer, you told as the points in your analysis of the report. Could you please explain the depth of the oil layer? The role.
So oil microscopes. I would like to speak louder. So as the droplet spreads, it actually drags the oil along with it. And this provides a distance expression. You could actually use this to solve for how the radius of the mother droplet, the larger radius of the mother droplet should be. And also when the final droplet forms, the flow of oil, because of the variability flow, is actually still outward, and it carries the outer droplets away. And this is the effect.
So just us check with you, Lily, if you drop the droplet from really high, what happens?
If we assume the process of dropping of alcohol is negligible, then now we can just consider it
I'm dropping the alcohol mixture from high.
Okay.
That's not negligible, right?
Okay. When it's not negligible, then the initial concentration of alcohol will be smaller in the consideration of putting in our theory, which will technically just be resulting in having a lower concentration of additional alcohol.
Sorry. Okay, so I drop it from higher up. I think it's going to have less alcohol because it's evaporated all the way down. Is that the right process?
Sorry?
Why does it have less alcohol in it? If I drop it from, a meter,
That the alcohol will not affect as much, and the phenomenon itself will only be affected due to the higher velocity of injection of droplet.
And so what happens?
It will go, when the velocity is high, it will go deep into the oil and then float up, and then continue to spread.
And so then it still spreads
Yeah.
in the same way.
Only if the initial concentration is high enough. When it's at the range that it's not high enough, for example, tested 50% isopropanol, you inject it into the oil, it flows, but it no longer spreads. However, if you just drop it in general, it does spread. So it affects, but only affects for the concentration with lower concentration of alcohol.
Okay, thank you.
Is slide number 70 or 60? I'm not sure. 16 or 17? 17. Oh, okay. Now, I want to know, according to your formula, the theory, you mentioned fixed law. Can you please explain?
The fixed law itself is the diffusion of the alcohol particles and its diffusion into the air. So we use that to represent the evaporation of alcohol.
Sorry, that could go on. Thank you very much. So we need to deliberate and plan on work out our schools. Thanks very much. I gave the 5. I gave, I gave the 5, their grades were 2.2 for report, 1.7 for the discussion, and because I was just, there was so much that was not explained, and we just went straight in there with all these equations and never really talked about what was being done enough to really link it all together, and I felt that was so often there was so many radii that I didn't know which radius it was, and I was just getting lost in all those graphs, and so I felt there was a lot of stuff there, but you fell down on the communication. But Farida liked it.
So my partial first of all, this part I gave her 4.5, and I especially like the discussion which she has with the opponent, and she's very much clear about all the ideas and how the droplet formation on the corner and so I can say is really for me is really impressive thing. So when I give 3 marks, which is the maximum in my score, because in this part I noticed she proved the deep understanding, again which is reflected not only in the presentation but also the discussion which she made with the opponent and the reviewers.
Do you want to carry on talking, because you were also Ms. Jensen when it came to the opposition, if you like that.
For opposition, I think it is as a report is quite comprehensive. So the opponent did a well job, and she basically brings there are something which is missing during the presentation, but she brings this in the notice of us that about the whole presentation. So this is what I to clarify the different aspect of the experiment. She has
That's not favorite of 4.
I gave the partial grading. I gave the 0.5 because she asked very few questions, 0.5 in this part. But the opposition speech with 2.5 and with the discussion with the reporters with the 2.5. And it sums up 6.5, but around 7.
Okay, I explain my for opponent. I saw opponent a bit passive. She not conduct discussion, and I give half point for aspiration, 1.5 for opposition speech, and 1 point for discussion for them.
And finally, the reviewer, Farida, again,
I basically rounded from 8.5 to 9. And the reason being is quite comprehensive report, and as a reviewer, the reviewer did a good job. He put forward the question like the effect of the oil thickness, and he also rightly mentioned that the two issues were not in the presentation, even though the presentation was very good. At this stage, he noticed the dynamics and the effect of the oil. So I like this person a lot because he critically analyzed the slides. That's why I gave the marks.
and I gave the lowest mark for the review. So I just, your questions were, came if there was something that you should have gone into. That was a 1 and a 2. quite good, but then the one, the review of opposition, which I didn't think you drew out quite so much. And again, there's discussion analysis. Got quite into using acetone, which wasn't very much part of the discussion really that you were reviewing. So, yeah, you went over time as well. So that was right. The 6 not bad, I didn't see the 9. But that's why we're all, you've got 5 of us getting a different point of view. Well done, everybody.